Thank you. So, I'm here to give a talk on nanomaterials development using artificial intelligence. Am I audible? So, as you heard from from my profile, I have little introduction to nanomaterials. So, in fact, you have all rights. So, you have all rights to question me in between if I make any obvious mistakes while explaining some aspects of nanomaterials which I am new to. So my focus is to give you an introduction to how you can get into a machine learning based or AI based research in problems related to nanomaterials. So even though I am new to the area, I hope I may be able to give you some directions on how to start with it. So let's begin with the definition of artificial intelligence. Anyway, it's not new to you, but still, I think to get a continuity in the discussion, it's better to start with a description of artificial intelligence. So it refers to development of any computer system or software that can perform tasks that typically requires human intelligence. Whichever system you see that you feel that only human intelligence can solve it, but a system is able to, a computer system is able to solve it. Those systems are artificial intelligence based. Nowadays, there is even in the industry, since industry tries to bring in the word AI in all aspects of a software, it can be a bit confusing. Many things which are not really artificial intelligence are termed as artificial intelligence. Right? So whenever you look at a system, you can call it as an AI-based system only if you see that it is mimicking or emulating human intelligence. So let's take a classical example of chess. I mean, computer playing chess. So some 20 years back or even before that, AI was involved in making a computer play the game of chess. So, but you may wonder how is that? So this is just to give you an idea how classical artificial intelligence was able to make such system, or in such classical AI system, what kind of logic was involved. Right? So let's try to understand. So basically, from a visualization point of view, this is what it does. What it means. So given some position of the chess board, what computer does is it computes all possible moves, right? To the extent it can afford. It computes all possible moves and then it decides which move is the best. Right? So from this diagram, you may understand that we are at some particular stage. Right? Let's assume that it's some stage S, and there are three possibilities in the next stage. And for each possibility in the third move or in the second move, there could be another possibility for each possibility, right? So it is basically it is 3 plus 3 square plus. So for 3 again 3. So it is it goes on like that. So if the computer wants to check for 10 future moves, then it has to do that much computation. But here in this system, computation is not the major challenge. Can someone tell me what could be the major challenge here? So if it is interactive, it would be nice because I'm going to talk for around 2 hours. And if I am attending it in the afternoon like this, I probably will get sleep. Right? So to avoid making you sleep, probably we can make it interactive. If some of you can move to the front rows, that will also be great, if you don't mind. So can you tell me what would be the major challenge here? The major challenge is in the memory, right? Why memory? Because the computer has to do this computations of 10 possible moves, and all those states have to be kept in the computer memory. Right? So that is anyway, that was a challenge in those days because the computers were having only limited primary memory. When I say memory, it means the random access memory or RAM, right, which the computer keeps the data temporarily. I'm giving the explanation to this level with the understanding that most of you are not from computer science background. So feel free to tell me if I have to skip some explanation, you can tell me. So this is an example of classical AI where it basically computes all possible moves or maybe all possible moves to the extent it is possible, and then decide which move is the best among the non-moves, right? So when you understand this logic, it is quite simple, right? But when you see it as an AI system, it is quite complex. But some of the AI systems are simple like this. But it doesn't mean that it is the logic is restricted to that. It is much beyond. So, but nowadays, of the AI systems, what you see are not really based on the logic which I have mentioned, or they are not really based on such rules, or maybe another better term would be heuristics, right? So the earlier chess system is basically a heuristic driven system, which means we can code this rule, we can program this rule, and then check for the best thing based on some optimization, etc., and then decide which move has to happen next. But nowadays, it is not purely such heuristic driven. So nowadays, it is mostly based on machine learning. So we'll check what is AI versus machine learning. So machine learning is in fact a subset of AI. So if someone says that machine learning and AI are different, it is not true. Machine learning is a subset of AI. So then what is machine learning? Machine learning deals with the statistical models which enables the machine to learn from data. Right? So it doesn't have any rules as such. We are giving the machine a data, and then we are asking, we have algorithms which are capable to learn from data, and given a new situation or a case, the system is able to tell us what has to be done or what it is. So so the rest of the talk will be mostly based on machine learning, because there is not much relevance for the classical AI at this point. What is more relevant is machine learning, which is statistical learning. So another better term in the mathematics domain would be machine learning is a little more a fancier term. A better scientific term would be statistical learning, but nowadays we commonly use the term machine learning or learning from data. So this is in short, we can talk about machine learning. We have a learning algorithm, and what is the input? We have a training data. And what is the output? It learns that expertise. The learning algorithm is capable to get that expertise. And then after the training, when we present a new data, it is able to predict or say something about it. So I like this human analogy, how we teach a baby to identify an apple. Right? So what we do is that we present all possible apples in different shapes. Maybe apples are mostly have almost the same shape. And maybe there is, to confuse the baby, we may even teach it, show it a green apple. Right? Green apple is also an apple, but usually apples have a reddish color. And then what we give to the baby is we give an orange or even a jackfruit to the baby and tell him or her that these are not apples. So this is what happens in machine learning. We present positive examples. At the same time, we present negative examples. Why we show them negative examples? Otherwise, so if you are showing to baby only the positive examples, sometimes if he sees a mango, he may confuse it with an apple. He says that it looks like almost like an apple. So it can be an apple. Even though he doesn't say this much, he may say that that's also an apple. So when we teach a baby, we probably present positive examples and some negative examples. This is what exactly we do in machine learning, simply speaking. So when we show him a new apple, which is the testing phase, we are testing the baby now. Now baby is learned, baby is the model. Right? Now we are giving a new apple and asking the baby what it is. And baby is able to answer it, that means our training is good. Otherwise, there is some problem with the training. Right? This is what machine learning simply means. Right? This is the simplest definition I think I can give you about machine. So this means there are possibilities where we can tackle problems in nanomaterials with machine learning. So we'll see some examples later. But before that, again, we'll go a little in depth to some aspects of machine learning. So let's take again another example where we try to bring in some statistical numbers here. So this is fish classification. I have taken it from the textbook by machine learning textbook by Duda and Hart. So those are the name of the authors. So that is why we have these names, which we are not familiar with. I'm not familiar with. I know salmon, but sea bass is some fish, and I don't know the Malayalam word. Since I got images of this, that's why I didn't compare sardine or mackerel, basically makki or lila. So that's why we have this example. So we are trying to classify, or we are trying to make a system to classify sea bass versus salmon. So when we try to classify a fish, so whenever we go to a fish shop, we identify fish by its shape, color, etc. So basically, those are the features, right? So some fishes have the same color, but we can identify them because of their height, length, and some the size of the eyes, etc. So basically, we are making use of such features. So in this image, you can see that they are considering height, length, and certain other features. So if you are going with manual system, right? So how do we generally identify a fish? I said that we know we have a rough estimate of its length, width, etc. So basically in our mind we construct a distribution like this. So what do we mean? Usually the salmon has we have some, let's say we have seen some 100 instances of these two categories of fishes. Based on these 100 examples we have seen, we probably make a model like this in our mind. Salmon generally the length is the x-axis, and the distribution, the count we have is the y-axis. Salmon doesn't have a length around the distribution is height towards less than 15, which means most of the salmon fishes have a length less than 15. It may be some 15 centimeter or maybe inches, and mostly, and there are some salmon which are more than 15 centimeters or inches. And sea bass, you can see that mostly it is more than 15 centimeters. And there could be some instances in our data, that is, we are considering some 100 examples of fish, which are less than 15 centimeters also. Right? So with this, we come to a conclusion. We come to a conclusion in our mind that generally this fish salmon has the length more than 15. And sorry, less than 15, and sea bass has length more than 15. Then we create a distribution on the lightness, right? How light the fish is. Then the salmon is lighter, sea bass is heavier. Sorry, the light. Sea bass is lighter, that is why it is high towards the in the x-axis. Salmon is little heavier. So we from the data we construct a distribution like this. So whenever we see a fish, since we have this model in our mind, this distribution very vaguely in our mind, we are able to classify it. So this is exactly what we are trying to automate with the machine learning. Right? So in this case, we have only two features, but probably in an actual machine learning problem, we may have many features so that we get accurate results. So in machine learning, what we may do is, we may consider, since we have two features, we can consider data instances as points in a 2D space, in a two-dimensional space. Right? So for example, if you consider this point, that means this is an example of a fish with lightness around 2 and width very close to 20. Correct? Width or length very close to 20. So we are considering two features, and we are plotting or we are representing our data in a two-dimensional space. So what most of the machine learning algorithm does is, I'm saying that most of the machine learning algorithms, not all the machine learning algorithms are based on partitioning a 2D space. Right? There are different types of algorithms, but most of the algorithms perform in this way. So what it does is, it finds the right partition between these two fishes. Right? In that case, there could be some, maybe there's some exceptions. You can see that it identifies this straight line. This is the right partition between salmon and sea bass based on these two features. But you can see that there are some 2-3 instances on the right side. It means that there could be some instances in our data which doesn't really follow the rule. Or maybe those can be considered as some outliers or exceptions. It does, so when we draw a line, or when the system, the algorithm draws a line, it doesn't mean that it has to perfectly match all the, it perfectly maps all the data instances. I mean, it should not, we cannot do that. Right? Wherever we draw a line, there could be some examples of salmon on the other side of it. Or there could be some examples of sea bass on this side of it. That happens. But we are drawing at a very optimal, at an optimum point where majority of fishes are classified correctly. So now what we do is when we get a new fish, we have the width and lightness of a new fish which doesn't belong to this training data. We see which side of the space it belongs to. So if it has, let's say that it has a lightness of 10 and then maybe a width of 90, that means it belongs to this side, which means we can classify it as a sea bass. Right? So this is how a machine learning constructs a model. It basically creates a partition between the data instances we have. Since this is a two-class problem, we have a single partition. We have many classes like this. We are classifying, let's say, 4 kinds of fishes. Then the partition would be different. The decision probably would be different. So here we have single partition and we see to which side of the space, to which partition of the space the data instance belongs to, and we say that okay, this is sea bass or this is salmon. Any questions here? So please feel to ask me any question because I have to make sure that you are in line with what I'm speaking. Yes.
Positive and negative data.
Yes, right.
So that's where the partition comes in.
Correct.
As I have.
Yeah.
So the partition comes between positive data and negative data.
Right. So in this case, you asked a good question because in the earlier example, I introduced this concept of positive and negative, and I didn't explain that when I explained this problem. So in this problem, we are classifying between two classes. One can be considered as positive and another can be considered as negative. Right? But what is the question you asked is, so we try to partition at an optimum point, which maximizes the number of sea basses on this side and number of salmons on this side. Let's assume that the algorithm is going to, instead of drawing a line here, if it decides to draw a line here, what will happen? Many of the salmons may get classified as sea bass. That's a problem. Right? Given the data we have, so we are given the data. So that is what we are given. Given this data, how can we maximize the chances of finding salmon on one side and sea bass on the other side? That is where the algorithm draws in. So the algorithm are written in such a way that the statement what I have made, that is the objective, that is the optimization objective, that is optimized. Right? So we should not have the number of salmons on the other side should be minimum. The number of sea bass on this side should be minimum. That is what we are optimized. Right? So I'm trying to make these statements in very plain English, but when we are represented using a mathematical formulation, it could be entirely different. But if you can understand this, mathematical formulation is not there. Is it clear?
But both of them are in the same positive side of the x-axis, the same quadrants. Both of the salmon and the sea bass, they are in the positive quadrant.
Yeah. So that is the positive quadrant, but we are drawing this line is what algorithm decides. So once this line is identified by the algorithm, then this is the model we have. When we get a new fish, we check, we compute the values between the width and the lightness of the fish, and then we check to which side of this line, the data belongs. Then if it belongs to this side, that means it is a sea bass. So
So
what
what we are trying to do, we are trying to assume that
we
we
have
have
an
an
automated
automated
classifying
classifying
system.
system.
The
The
fishes
fishes
are
are
caught
caught
and
and
then
then
it
it
is
is
passed
passed
on to
on
a
to a
conveyor
conveyor
belt,
belt,
and
and there
the
is a
camera
camera
is
at
somewhere.
somewhere.
The camera
Camera
captures the
captures the
image
image
and
and
computes
computes
the
the
length
length
and
and
lightness,
lightness,
and
and
maybe there
maybe
is
there
some
is some
other
other
machine
machine
to
to
compute the
compute the
lightness.
lightness.
Can
Can
we
we
automatically
automatically
place
place
them in
them in
two
two
different
different
trays?
trays?
This is
This
the
is the
automation we
automation
are
we are
trying.
trying.
Right? So
So
initially I
initially I
thought
thought that
when
when
we
we
go
go
into
to a
figure
fish
out
shop,
how
how
do
do
you
you
identify
identify
a
a
fish,
fish?
we are
We are
trying to
trying to
automate
automate
the
the
same
same
thing
thing
with the
with the
help of
help of
machine.
machine.
So
So
that
that
so when
when
the
the
fisherman
fisherman
catches
catches
fish,
fish,
they
they
won't
won't
get it
get it
separated
separated
from the
from the
sea.
seed.
Right?
Right?
They will
They
get
will
it
get
all
it all
together.
together.
So if
So
we
if we
have a
have a
system
system
like
like
this,
this,
we can
we can
automatically
automatically
separate
separate
the
the
fishes
fishes
and
and
keep
keep
in
in
different
different
trays
trays
and
and
then
then
carry
can
it
be
to the
sent to the
market.
market.
So this
So
is
this is
an
an
example
example
of
of
such
such
scenario.
scenario.
So
So
let's
let's
try
try
to
to
represent
represent
this
this
better.
better.
So
So
here
here
we are
we are
trying
trying
to
to
understand
understand
predictors
predictors
and
and
performance.
performance.
Predictors can
Predictors can
also be
also be
called as
called as
features.
features.
So
So
generally
generally
predictors of
predictors of
features are
features are
expressed
expressed
as
as
x1,
x1,
x2 up
x2 up
to
to
p,
p,
xp,
xp.
right?
Right.
So in
So
our
in our
example,
example,
what is
what is
p?
p?
In our
In our
example, what
example,
is
what is
p?
p?
It is
It is
1,
1,
2,
2,
3,
3,
4.
4.
Huh?
Huh?
Tell me
Tell me
loudly
loudly,
number.
no?
If you
If you
can
can
turn
turn
on the
on the
mic,
mic,
you
you
can
can
turn
turn
on the
on the
mic.
mic.
What is
What is
p?
p?
2.
2.
Yeah.
Yeah.
Why it
Why?
is 2? Because
Because
we
we
have
have
width and
and
lightness.
lightness.
But
But
depending
depending
upon the
upon the
complexity of
complexity
the
of the
problem,
problem,
we
we
may
may
go up
go
to
up to
maybe
maybe
there are
there are
problems
problems
where
where
we
we
use
use
1000
1,000
feet,
feet.
right? So
So
and the
and the
response is
response is
y,
y,
which
which
means
means
y
y
is
is
basically we
basically
are
we are
classifying
classifying
it
it
as
as
is it
is it
salmon
salmon
or
or
sea bass.
seagrass.
That is
That is
y.
why.
Right?
Right.
So
So
this is
this is
just
just
to
to
introduce you how
how
we
we
to
to
represent it
represent it
mathematically.
mathematically.
So
So
here we
here we
have
have
p is
P is
2,
2,
x1 is
X1 is
length,
length,
and
and
x2 is
X2 is
lightness,
lightness,
and
and
y
Y
is it
is it
salmon or
salmon or
sea.
seagrass.
So
So
basically,
basically,
what we
what
are
we are
trying to
trying
do
to do
is
is
we are
we are
trying to
trying to
when I
when I
say that
say
we
that
are
we are
drawing
drawing
this
this
line,
line,
it
it
is
is
trying
trying
to
to
identify
identify
a
a
function
function
f
f
of
of
x.
x.
What is so?
So
What is
what is
x
x
here?
here?
X is
X is
x1 and
x1 and
x2.
x2.
We are
We are
trying to
trying to
identify a
identify a
function
function
f
f
of
of
x1
x1
comma
comma
x2,
x2
so that
so
we
that we
can
can
predict
predict
whether
whether
it's
it's
salmon or
salmon or
sea.
seagrass.
So we
So we
have a
have a
true,
true,
or we can
we
say
can
that
say
we
that
have
we
a
have a
true
true
underlying
underlying
function
function
which we
which we
don't
don't
really
really
know how
know
to
how to
compute
compute
that.
that.
So when
So
we
when we
use
use
machine
machine
learning,
learning,
we
we
sometimes
sometimes
may
may
not
not
reach the
reach the
actual
act
function because
because
of
of
many
many
reasons.
reasons.
Right?
Right?
For
For
example,
example,
when we
when we
depend on
depend
two
on two
features,
features,
there
there
could
could
be
be
some
some
or
or
other
other
features
features
which
which
decide
decide
what
what
that
that
fish is,
fish is,
which we
which
are
we are
unaware of.
unaware of.
Right?
Right?
Because we
Because
are
we are
unaware of
unaware of
that,
that,
we
we
probably
probably
build a
build a
model
model
with
with
just
just
two
two
features.
features.
But
But
ideally, we
ideally, we
need
need
three or
three or
more
more
features.
features.
So in
So in
that
that
case,
case,
we are
we
a
are a
little
little
away
away
from
from
the
the
actual
actual
function,
function,
the
the
actual
actual
function
function
in
in
reality.
reality.
So
So
f
f
of
of
x
x
is
is
the
the
actual
actual
function in
function in
reality.
reality.
With
With
machine
machine
learning,
learning,
what we
what
are
we are
trying
trying
to
to
do
do
is
is
we
that
are
we are
trying
trying
to
to
estimate
estimate
that
that
f,
f,
which
which
we
we
call it
call it
f
f
cap
cap
x.
x.
This is
This
a
is a
little,
little,
this is
this
in
is in
fact
fact
a
a
little
little
bit of
bit of
philosophical
philosophical
angle to
angle
the
to the
problem of
problem of
machine
machine
learning.
learning.
You
You
don't
don't
really
really
have
have
to
to
worry
worry
about
about
it.
it.
What
What
I'm
I'm
trying to
trying to
say is
say is
that
that
whenever we
whenever we
use
use
machine
machine
learning
learning
to
to
compute a
compute a
function, to
function, to
identify a
identify a
function,
function,
to
to
classify
classify
something,
something,
it
it
may
may
not
not
be
be
the
the
actual
actual
function we
function we
expect in
expect in
reality.
reality.
It
It
may be
may be
slightly
slightly
different
different
from
from
that.
that.
Right?
Right?
So we
So we
call it
call it
f
f
cap of
cap of
x,
x,
which is
which
an
is an
approximation or
approximation or
estimate of
estimate
the
of the
true
true
function
function
f
of
of x
x
based on
based
the
on the
observed data.
observed data.
So the
So the
challenge is
challenge is
that
that we
we we are building this classifier or this f of x, f cap of x, based on the data we may have, let's say, 100 examples of species or maybe 1,000 examples. But if we have, let's say, if we have 10 million examples of fishes, probably we may be very close to the actual F. But when we have only few examples, our estimate will be farther from the actual the functional reality. That's what I was trying to say. So there are different types of machine learning. Whatever we are explaining mostly was supervised learning, which means there is a supervisor, which means there is a training data and the algorithm is trained with some data. And there is unsupervised learning and reinforcement learning. Let's try to have a basic understanding. So, In supervised learning, we have, as I mentioned, there is a training data. Right? We have n examples. Let's say if we have 100 examples, n is 100. We call it as a setup of xy, xi, and yi, where xi is the set of predictors, right? Which could be again xi1, xi2 up to xip, and yi is the classification, non-classification. So if we have 100 fishes, we have two features of each. That means we have x11, x12, and then y1 is, let's say, maybe salmon or sea bass. Again, we have second data which is x21, x22, and then y2 is again salmon or sea bass. That's how we arrange the data. And we pass this training data to a supervised learning algorithm. We have the training. Once we have the model, when we have a test data, we pass the test data to get the predicted labels or values. So we do training first, we get the model. So this is similar to what I explained earlier. And then now we have a test data which the model has not seen before. And then when we give the test data, it classifies what class is it the salmon or sea bass. So that is called prediction or testing. So the point is that the training data have labels here. So in supervised learning, the training data will have corresponding labels. As the example of fish classification, we have 100 examples of fishes and we know what type of fishes. So these are examples of supervised learning. So the first problem is this is not a regression. This is classification as we have seen in the fish classification. Right? We given a data, we classify. We say whether it is sea bass or star. But in this problem, we are not classifying. We are predicting a value corresponding to the input data. So let's assume that given the market conditions today, what is the price of the stock of Tata Steel? Right? In that, it is not a classification problem. We are predicting a value for the stock value for the stock of Tata Steel. So let's take a classification, so supervised learning problem in anatomy. So this is basically an example problem. So we have some data. The problem is classify a nanomaterial as metallic or semiconductor. Right? So we have some, let's say we have a data is very small. We have 4 data instances and we have some features with its composition, the size in nanometers, the shape of the nanomaterial, and we have the class, whether it's metallic or semiconductor. Right? So as we have seen, since we have 3 features, we can consider these points, data instances, in the 3D space, right? Because we have 3 features. We have composition, we have size, and we have shape. And now the task of the machine learning algorithm is to identify a plane between these points so that we ideally classify the metallic nanomaterials and semiconductor nanomaterials. This is to give you an example in the context of nanomaterials. So generally in supervised learning examples, you might have seen all these examples. Email spam filtering. Right? When you get the email, sometimes it may go into the spam. So the Google or Yahoo classifies it with the help of machine learning algorithm. So it is trained with spam mails and non-spam mails, and it classifies whether a mail is spam or not. Speech recognition, that is converting the input speech into the text. That's the supervised learning problem. Machine translation, that is automatic translation from one language to another, is a supervised learning problem. And you may be familiar with all of this. So the next category is unsupervised learning. So the first is supervised learning, where the data we have labels associated with the data. So second is unsupervised learning, which means we have a set of fishes. We are seeing a set of fishes. We don't know the name, but based on the features, we are able to identify which category it belongs to. We are not able to name the category. We don't know whether so now we can say one is prawns and one is something else. But assume that a small child is seeing this, and if we ask them to classify, he doesn't know the name, but with the help of the shape and color, he is able to segregate both these kind of fishes. Right? This is what unsupervised learning does. Basically, it identifies there are two clusters. So in some problems, we will have to go with unsupervised learning, where we don't do any training with the labeled data. We have some data. We do some categorization, and when we get a new data, we say that to which category it belongs to or which cluster it belongs to. We do not really name it. So those classes are that set of problems belongs to unsupervised learning. So generally, this is how it is done. Mathematically speaking, if we have some set of data, we assume and we know that there are three clusters. So that is some information we should have in some cases. We should have an idea how many different categories or clusters are there in it. So if we know that there are three clusters, what we do is that we decide three centroids for the day, three mean values for the day. And then based on the distance, we rearrange it. And finally, after few iterations, we reach a conclusion about the clusters. So this is a very short description of our clustering or unsupervised learning algorithm works. Not in all cases, but most of the cases. Okay, so let's have a discussion about nanomechanics. So, in fact, I thought once again. Yeah, I forgot to include some slides of reinforcement learning. So I will give you a discussion. I thought I included those slides. So reinforcement learning is another category where the learning is a little different. It's based on rewards. Right? So we do not have a training data as such, but we have some states and some possible actions from the state. And when an action is taken, if it is a positive output, then we give a positive reward. If the action is leading to a negative impact, then we give a negative result. So it is very much analogous to how a baby learns to walk. We try to teach him or her, but it's not really, it doesn't happen by our teaching. It happens with reinforcement learning. So it tries to stand up, and then when the baby tries to make a step, if he is successfully understanding, he automatically learns what kind of muscle movement or leg movement he has to perform to make that successful. So if he's falling, then he corrects it automatically. This happens as a repeated process, and finally he learns to walk. So this is exactly what happens in reinforcement learning. But the challenge is we have to define these state actions and what are the possible outcomes, and based on the outcomes, what negative reward, how much, what is the degree of negative or positive reward we have to give back to the system based on the research. So it is easier to understand based on how a baby tries to baby learns to walk. So this is something which you are more familiar with. You know that nanomaterials, the dimension is measuring from between 1 to 100 nanometers. That's why it is known as nanomaterials. It can occur naturally or artificially, which are specifically designed to exploit unique optical, magnetic, electrical, and mechanical properties. So the precise control of size, shape, surface properties during synthesis is fundamental to nanomaterial development. So in fact, all these aspects are kind of key to what problems are, what machine learning problems are there in nanomaterials development, characterization, or classification. Right? So this is just to give an introduction. So when it comes to machine learning and nanomaterials, these are generally the kind of problem, not limited to this, but these are generally the kind of problems we have in machine learning applied to nanomaterials. So we have predictive modeling, basically property prediction. So ML models can predict the
the
properties of
properties of
nanomaterials,
nanomaterials such
their
as their
optical,
optical,
electrical,
electrical,
and
and
mechanical
mechanical
behavior.
behavior.
I've
I've
seen
seen
that
that
we
we
have
have
some
some
set
set
of
of
nanomaterials,
nanomaterials,
and
and
we
we
don't
don't
know.
know.
We have
We
to
have to
understand
understand
some
some
of
of
one of
one
these
of these
properties.
properties.
So
So
we
we
have a
have a
large
large
amount of
amount of
data
data
for
for
which
which
we
we
know
know
the
the
property.
property.
A
A
machine
machine
learning
learning
algorithm
algorithm
can be
can be
trained
trained
with
with
that
that
data,
data,
and then
and then
given a
given a
new
new
nanomaterial, we
nanomaterial, we
can
can
predict
predict
one of
one
these
of these
properties.
properties.
Next is
Next is
material
materials
discovery.
discovery.
So this
So
is
this is
one
one
uh,
uh,
competitive
competitive
area
area
where this
where
could
this
be
could be
useful.
useful.
So
So
it
it
can.
can.
So
So
the
the
advantage
advantage
here
here
is it
is it
can
can
reduce
reduce
the
the
application of
application of
machine
machine
learning
learning
in
in
this
this
problem
problem
can
can
reduce
reduce
experimentation
experimentation
a
a
lot.
lot.
That's
That's
what my
what my
understanding.
understanding is.
So
So
based
based
on
on
the
the
properties
properties
of the
of the
available
available
nanomaterial,
nanomaterials,
the
the
nanomaterial
nanomaterial
composition,
composition,
we
we
can
can
discover new
discover new
nanomaterial.
nanomaterials.
Right?
Right?
So
So
what our
what our
data
data
will
will
have?
have?
Our
Our
data
data
will
will
have
have
large
large
amount
amount
of
of
nanomaterials
nanomaterials
and
and
compositions,
compositions,
properties,
properties,
whatever
whatever
features or
features or
whatever
whatever
properties we
properties we
can
can
have will
have
be
will
our
be our
data.
data.
And
And
then
then
based
based
on
on
this,
this,
if we
if we
say that,
say
okay,
that
I
okay, I
want a
want a
new
new
nanomaterial
nanomaterial
having
having
these
these
properties,
properties,
then
then
the
the
machine
machine
learning
learning
system
system
should
should
be
be
able
able
to
to
come up
come
with
up
a
with a
new
new
composition
composition
which
which
doesn't
doesn't
exist
exist
based on
based
the
on the
survey.
survey.
Right.
Right.
Otherwise,
Otherwise,
my
my
understanding is
understanding is
that we
that we
probably will
probably will
have to
have to
do,
do,
you
you
can
can
correct me
correct
if
me if
I'm
I'm
wrong,
wrong.
we
We
probably will
probably will
have to
have to
do
do
uh, a
a
large
large
number of
number of
lab
lab
experiments
experiments
to
to
ensure
ensure
that
that
these
these
composition will
composition will
have
have
these
these
properties.
properties.
Right?
Right?
You
We
have
have
machines,
machines,
some
some
sort of
sort of
electron
electron
microscopy,
microscopy,
etc.,
etc.,
to
to
analyze the
analyze the
properties.
properties.
So
So
you
you
keep
keep
trying
trying
doing
doing
trial
trial
and
and
error.
errors.
So
So
machine
machine
learning
learning
algorithms to
algorithms to
some
some
extent
extent
help us
help
to
us to
narrow
narrow
down
down
this
the
search.
search.
So what
So
is
what is
narrow
narrow
down in
down
the
in
search?
search?
With
With
machine learning,
machine
machine
learning
learning algorithms
algorithms
won't
won't have,
may,
so
may not
may
be
not
able
be
to
able to
say
say
very
very
precisely
precisely
that
that
if
see
you
if you
have
have
if you
if
have
you
a
have a
nanomaterial
nanomaterial
based
based
on
on
copper
copper
and
and
something
something
else, it
else
will
will
give
give
you
you
a
a
nanomaterial
nanomaterial
of this
of this
property.
property.
Right?
Right?
But you
But
can
you
say
can
that
say
see,
that see with
with
this, with
some
some
80%
80%
probability
probability,
will
will
this
this
composition will
composition will
give
give
you
you
this
this
property.
property.
So
So
instead of
instead
doing
of doing
100
100
experiments,
experiments,
probably your
probably your
experimentation
experimentation
can be
can be
reduced to
reduced to
10 or
10 or
20,
20,
and
and
then you
then you
can
can
analyze the
analyze the
properties of
properties of
the
the
result of
result of
those
those
10,
10,
20
20
experiments.
experiments.
That is
That is
where the
where
machine
machine
learning can
learning
be
can be
helpful
helpful
in
in
nanomaterial
nanomaterials
discovery.
discovery.
Another
Another
problem is
problem is
optimization.
optimization.
So
So
how
how
can you
can
do?
you
So
do?
the
So the
nanomaterial
nanomaterial
synthesis
synthesis
is can be
can be
very
very
expensive
expensive
or
or
can be
can be
sometimes
sometimes
very
very
time
time
consuming.
consuming.
So
So
by
by
making
making
use
use
of
of
machine
machine
learning,
learning,
probably
probably
you will
you will
be
be
able
able
to
to
optimize
optimize
certain
certain
steps
steps
or
or
certain
certain
processes in
processes
that,
in that,
and then
and then
that
that
can
can
lead
lead
to
to
optimization and
optimization and
cost
cost
reduction in
reduction in
nanomaterials.
nanomaterials.
So
So
this is
this is
what
what
synthesis
synthesis
optimization
optimization
is.
is.
So
So
next is
next is
characterization.
characterization.
So we
So we
can
can
characterize
characterize
or
or
analyze
analyze
or
the properties,
automatically
automatically
analyze the
analyze the
properties of
properties of
nanomaterial.
nanomaterial.
It
It
can
can
even
even
help
help
to
to
recognize the
recognize the
patterns.
patterns.
So
So
that
that
means
means
if
if you want to
we
if you
want to
want to
categorize
categorize
the
the
proper
the
the structural
structural
properties
properties
of
of
nanomaterial.
nano,
Given a
given a
nanomaterial, we
nanomaterial,
are
we are
not
not
sure
sure
what
what
structural
structural
property it
property it
has
has
or
or
which
which
whether
whether
what
what
structure
structure
it
it
has.
has.
With the
With the
help of
help of
some
some
machine
machine
learning
learning
algorithms, we
algorithms, we
can
can
do
do
it. I
it. I
have
have
few
few
examples in
examples
the
in the
coming
coming
slides.
slides.
Not
Not
all of
all of
these
these
problems,
problems,
but
but
some of
some
these
of
problems.
problems.
So one
So
of
one
the
of the
simplest
simplest
problem I
problem I
could
could
to
to
start with
start
I
with
could
I
get
could get
is
is
predicting
predicting
the
the
band
band
gap
gap
of
of
a
a
nanomaterial.
nanomaterial.
So
So
this is
this
to
is to
understand
understand
whether
whether the
nanomaterial
nanomaterial
behaves like
behaves
a
like a
conductor,
conductor,
semiconductor,
semiconductor,
or
or
insulator.
insulator.
So this
So
is a
this is a
machine
machine
learning
learning
problem.
problem.
So
So
Here, the input features are structural descriptors like atomic composition, bond length, coordination number. So if you ask me what are these, I don't have a clear explanation. You may know better than me on these features. So can you tell me, if this is the problem and this is the features, what is the first step we will have to do to solve this using machine learning? So we know that these three are the features, and we want to build a model, a machine learning model to predict. So given a new material, you have to predict the bandwidth. So the first question is it a classification problem like classifying the fish, or is it a regression problem like predicting a value? Since you know about band gap method, you can answer. So is it a classification problem where we predict what kind of fish it is? Or is it a regression problem where we predict the value as an output? Can someone tell me what problem it is? Yeah, why is it regression? Yeah, it's the other way. Sorry. The other way. Your right answer is correct, but based on the problem, we are predicting the band gap, which is basically a value, some electron volt or something. So it predicts the value. So it is a regression. We are not classifying. We are not classifying it as a semiconductor or insulator. Instead, we are predicting the band gap. Based on the band gap, you can identify whether it's a conductor, insulator, or a semiconductor. Right? So here, this is what we do. Basically, I'm kind of sort of repeating certain steps which we discussed earlier to give you a better idea. So we have a training data. So what is the training data we have? We have some these properties. I'm giving you pictorial representation of the data. We have these properties of, let's say, some 1,000 nanomaterials. That is our training. We train the learning algorithm with this data, and during the testing phase, we give the structural descriptors or the properties of these properties of a new nanomaterial, and then we have to predict the band gap. So the expectation is that if we give a new nanomaterial, it is not there in our training data, the model should be able to predict the band gap value of that nanomaterial with high precision, with high accuracy. Right? That is our expectation. Any question?
So training data, how if you are getting the training data from the journals,
so that the source could be anything. So assume that you have maybe you can collect this data from the journals, or assume that there could be some repositories where these kind of structural data is available. Right? So if you search for data sets, not just for nanomaterials, even for other problems, there are sources where we get large number of data. So if you search for this problem, so data sets for band gap prediction or band gap computation, you may get data for that. So if we have, then there could be data sets with 1,000 data instances, there could be data sets with millions of data. Right? So when we have large amount of data, what is guaranteed is we'll definitely have a better model, which means our model will predict with higher accuracy.
new material, what can be training data we can.
Okay, that is the problem. So what we are assuming is, if we have large number of data in our training data, our data set, and then we train a learning algorithm, it should become capable to predict the band gap value of a new material. If the new material band gap value is already in training data, then there is no point. You don't need to predict this problem. So these kind of machine learning problems are relevant. And we don't know a new material, when we do not know the band gap value of a new material, and we do not have a large setup to compute the band gap value, we are trying to solve it statistically. If we know the band gap value of large number of thousands, large number of let's say thousands of million materials, can we predict the band gap value of a new material? But you may ask how it is possible. Right? It is something like you know the taste of some curry, one curry. You want to predict the taste of curry with the experience of these two curries. How do you do that? You know the taste of fish curry, you know the taste of sambar, you know the taste of let's say rasam, and when a new curry is introduced to you, sometimes you may be able to predict the taste of that curry. How it is possible? How it is possible? Ingredients, right? So here the same thing works. What is the ingredients here? The features of the properties of the nanomaterial is the ingredient. Since we are training the algorithm with not just, we are not saying that this nanomaterial has this band gap. What we are presenting? We are presenting with all the relevant properties of the nanomaterial, and then giving the band gap. So when you introduce a new material, based on its similarity to the other nanomaterials in the available data, it is able to predict the band gap. Right? So assume that you are trying to predict the band gap value of some nanomaterial based on germanium, and you have the band gap value of some material based on silicon already in the data. Since I'm not very sure, if silicon and germanium have some high similarity based on the properties, then the learning algorithm will be able to say that this point is very close to this particular data. That is when, let me go back to this slide. Plotting or understanding the point in 3D space is important. Right? Assume that, let's forget CBAS and SALA. Assume that this data instance is an instance of silicon. And when you get a new material, let's say germanium, assume that based on its properties, in this some n-dimensional space, if that is very close to this material, that means that may also have a similar band gap. Are you getting it? So anyway, I will explain that further. So to understand this problem better, it is good that you are asking questions so that I can understand what has to be explained further. So this problem is not a linear regression. This is a linear regression because we are assuming that the relation between the features is, or like relation between the features and the output value is linear. So here for simplicity, let's assume that we have only one feature. In the x-axis we have feature and y-axis we have band gap. So these are the data instances. These blue dots are the data instances that we have in the training data. So from the image, can you tell me what we are trying to do here? This is a simple statistical problem. Linear regression is, even though the term is mostly still machine learning, it is not new to mathematics. Maths belongs to, it is a fundamental technique in statistics. So can you tell me what we are trying to do here? Now we can be louder. It is wrong.
Probability of finding more.
Okay, so all these answers are almost correct, but that's a slide. What we are doing is, we have the data points. We are trying to fit a line to the data. So why we are fitting the line? We are identifying the trend. So if you identify the trend, what is the advantage?
Predict.
Yeah, we can predict. Right? So that means we have these many data points. Right? If we have, assume that we don't have this red line, we have not computed the red line, which is basically fitting the line. We have not done that. When we get a new data point with this feature 1, some value of feature 1, how do we identify the corresponding band gap? See, let me repeat. I'm plotting this in 2 dimensions to make it simple. We have many features. When we have many features, we have n-dimensional to make it visualize. That is why we have just one feature. We assume that the band gap is dependent on just one feature. Right? So if you don't have this line, when we get a new point, we have no clue how to predict the band gap value. So what we are doing is a simple technique of linear regression. What it does is, it identifies the best possible line, the equation of a line, which can best fit all this data. Right? So basically what it does is, it computes an equation like this. This is basically the equation of a line, which is mx plus, you may be very familiar with mx plus c, but here instead of m, we have w1. And x is feature 1. We have a y-intercept, which is b. Right? So during, can you tell me while training, what we are learning here? we said we are going to train with this. What component of this equation gets trained? So this understanding can be helpful in understanding some basic preliminary concepts in machine learning. And then it will be easier for you to apply to your problems. You understand? That's why I'm asking. Then we have the mathematical formulation of linear regression for this particular problem. So when we say that we train this equation with this data, I'm making it using simple terms, but not really say that we are training the equation, we are training the model. What aspect of this equation or what component of this equation gets trained or learned? Any idea? Feel free to tell me any random answers. In fact, I have enough time. I don't have many more slides. I have enough time. Yes. If you do not mind, can you turn on your mic? What gets learned? Okay, let me simplify the question. Does W1 gets learned or feature 1 gets learned or B gets learned? Okay, band gap is what we have to predict. So what gets learned? Feature gets learned. Feature doesn't get learned because that is the input. Right? That is the input. If you treat it as a program, if you treat it as a computer program, feature 1 is the input. In the training data, we have feature 1 of some, let's say, some 1000 different nanometers. And from the and what it learns is it basically learns W1 and B. So when we say that in the equation of lines, we learn the value of W1 and B, that means we are able to say, we are able to define the line, right? So in the equation of a line Mx plus C, what defines the line? We need only two things. We need the slope of the line, we need the y-intercept of the line. Once that is clear, we now know the line. You can extend it. Got mic. So it can get extended to any point, right? Even if you have a value beyond 70 or 100, you are able to predict the band gap value because you are not restricted to the data, right? You have an equation which you learn from the data, and it can identify the band gap of corresponding to any value for feature. So during this training with this data, what it basically learns is it learns the slope of the line, that is here in this case W1. So in the context of machine learning, we call it as weight. So we call it the weight of feature and the y, or we call it bias. In machine learning terms, we call it this is weight and this is bias. Why I introduced the equation of line? Because it is easier for you to understand based on higher secondary mathematics. Right? So based on the available data, we are learning the equation of the line, and once the equation of the line is learned, now we don't need this data. We can throw away this data. Given a new point, let's say that I want to predict the band gap value of some nanomaterial with feature 1 value as 25. I can if 25 is here, and corresponding to that on the line, the value is somewhere around, let's say, 7 or 8. So the band gap is 8. So that is what we do with linear regression. But here there is a constraint. Right? The constraint is we have to ensure that if we are applying linear regression, we have to ensure that the relationship between the features and the output value is linear. So instead of this, the data looks like the data is coming like this, and then there is a dip here and going like this. Then a first degree equation of a line doesn't work. You need a second degree polynomial. Right? Then you try to fit in second degree polynomial instead of first degree line. Is it clear? Any questions? So with the help of the problem of predicting the band gap value, we try to understand linear regression. So the final takeaway of this discussion is whenever you have a problem of predicting a value, you can see whether linear regression or linear regression is not applicable or some other higher dimension, higher degree polynomial regression will be helpful. Right? So this is just to give an understanding. When you see a problem related to predicting a value, you can now think, can I apply linear regression with the help of some available data and use that for predicting the whatever value. So generally we can have a generic formulation like this. When is this applicable? Sigma wi into feature I plus b. When is that applicable? So we discussed this. We have the constraint of visualization is always restricted to 3-dimensional. We cannot draw anything beyond 3D. I gave an example with just one feature. But when you have multiple features, the equation of linear regression will look like this. You basically add W1 into feature 1 plus W2 into feature 2 and Wn into feature n plus. That's what this equation. Right? So instead of a line in this 2D space, it will be line n plus 1 dimension. Why it is n plus 1 dimension? Because when you have one feature, you can have a line in 2-dimensional space. When you have n features, you have a line in n plus 1 dimension. So should we go for a break?
Can you TI or 245? Okay.
Okay, let's discuss another problem, which is structural classification in nanomaterials. So I'm picking certain problems to explain certain categories of machine learning algorithms so that the understanding that will be helpful in applying those algorithms to certain non-problems that you may be familiar with. So here the example problem is identify the structural classes of silver and copper nanopart. So from the paper describing this approach. Sorry, I forgot to just one second. Okay, somehow I had the citation of the paper which describes this. So this approach is basically from a paper which discusses the problem of identifying the structural classes of silver and copper. So the paper says that I have not understood it completely, to be honest. The paper says that they have some large number of different nanomaterials based on silver and copper independently. I'm not saying that there are nanomaterials which have copper and silver, but I don't know such nanomaterials exist or not. Maybe so and so can come.
Silver and copper are
available. So they are discussing, my understanding, and they are discussing about nanomaterials were based on silver and another set of nanomaterials based on copper. So what they are trying to identify is what are the different structural classes within these nanomaterials. So depending upon the atomic composition or something of these nanomaterials, the structural classes, how the atoms are structured or connected in these nanomaterials are different. So there are five major structural classes phase rendered with icosahedral, decahedral, a mixture of icosahedral and decahedral, and amorphous. So these are the major structural classes. So how do they understand? How do they understand the features? What is basically the feature extraction here? So they make use of some technique called as common Weber analysis. And then they analyze the local atomic environment of this nanomaterial. So that's how they do the feature extraction. So till now, when we were explaining the data, we were saying that we know the features. Right? So in this case, what they are doing is that they are using some machines or something to get these features based on common Weber analysis to get the local atomic environment of the nanomaterial. So these are some of the non-structural classes. But here in this data, we do not know in the training data, we do not know what class it belongs to. So here the problem is that we have some, let's say, some large number of nanomaterials, different nanomaterials based on copper and silver, but we do not have any idea about what are the different structural classes present in it. So in such a case, let me ask you this question: do we apply supervised learning or unsupervised learning? What sort of learning we apply? Is it supervised learning or unsupervised learning? Unsupervised, right? So because in supervised, we have labeled data. So if it is a supervised problem, you have labeled data. Each nanomaterial, we know what structural class it is. And whenever we provide a new material, it is able to say. But here the problem is not predicting the structural class of a new material. Here the problem is, given a large number of, we have a large number of nanomaterials, we do not know anything about the structural classes of these materials. We want to separate them based on the structure. Maybe after separating them by taking one or two samples, we can say that this is face-centered cubic or icosahedral or decahedral. But we do not have any information about that, about the data at this point. Right? So here we don't have feature extraction, so we use a technique based on common linear analysis to extract the features. So what is the data? Data is each data instance could be a structure of silver or copper, and it represents a 33-dimensional vector. It is not a single feature. We have 33 features. And each dimension represents the DNA signature. I'm not going into the depth of that. I got a basic understanding of what is DNA signature. So DNA signature is to what percentage of a particular atomic composition is present in that dimension. So there are 33 different signatures, 33 different compositions. So this, after DNA analysis, it says how much percentage of each DNA signature is present in the data, right? In that particular nano. So that's what the feature represents. So I'm giving you this idea, this example, to give you an understanding of how each data set differs. Right? In the previous case, we discussed a very simple problem of band gap prediction with the features. In this problem, we are trying to identify cluster based on the structural classes, where each data instance is a 30-dimensional feature, and each dimension is a percentage value of the CNA sequence, some atomic. That means in a particular nanomaterial, there is different atomic compositions present, and it has its own strength. In some nanomaterial, maybe the first signature is 10% strong. In some other nanomaterial, the first signature is, let's say, 50% strong. So that's what the feature is. So here, like we have explained earlier, we cluster it into some clusters and then identify what are the different clusters of different structural classes present in the data. And then this is kind of a discovery approach where we are trying to, we do not know much about the materials. We do not know much about the silver and copper nanomaterial. We are trying to discover some new aspects of these nanomaterials. That is where this kind of unsupervised learning can. So again, to repeat the data can be considered to be in a 33-dimensional space. Right? We have a 33-dimensional vector. So we now have to assume that the given data can be one point in a 33-dimensional space. And this particular study, in this paper, they discovered 5 structural classes of silver and copper, and 14 detailed subclasses for silver and 15 detailed subclasses of copper. So I'm just keeping the results there. So there is another paper authored by Rogalia from 2023. Also discusses the same methodology for identifying structures. So these are very much related papers. So since both explains almost the same approach, I thought of keeping. They have, so if you read this paper, they have some more finer details of experiment, which would be a little difficult to understand, or maybe you may have to read it a few times to understand that. So I have just explained the very top level idea behind, or methodology behind this paper. So let's get into the problem. Basically, it is a nanomaterial classification. So in this particular problem, so this is a paper by Cabrera, Carlos, and al. So which is the paper is based on paper presented as classifying nanostructured and heterogeneous material from transmission electron microscopy images using convolutional neural nets. Right. So basically, the problem here is classify a nanomaterial into silicate, silica, or protein. Right. So there are three classes here. So what is the data set here? Here the data set is slightly different. Here we have high resolution transmission electron microscopy images capturing the complex internal structure of nanomaterials. So with this, so what I understood is with this imaging electron microscopy, we can get the internal structure of nanomaterial. And here they use a neural network architecture based on convolutional neural network to classify the nanomaterial silica. Okay. So at this point, we are quickly jumping to another class of machine learning algorithms known as neural networks. You might have heard. That is what. So neural networks. In fact, nowadays neural networks are much superior to other machine learning methods in the field of artificial intelligence. But I think before that, since it's a few continuous discussions to be had, let's take a break at this point.
Any questions?
And if you have any questions,
the temp images, how can we, are you going to continue with the temp images or?
yes, but so before that, I'll try to explain neural networks.
Okay.
That takes some time.
That also will be explained a little about that.
So we're not going into the details of temp images.
So the session is now open for discussion after this. You please interact. Or the possibility of doing things based on our research personally, please ask questions. Or
You can ask open questions also, because I would like to make a stop here so that next session of discussion will be heard. Yeah.
Which they are using, because we have data sets, where we have to upload the data, give this kind of regression or some kind of methodology.
So that's a good question. So for some of the basic methods, we can use. If you are going to, maybe we should have. We may have to do some basic program. Right? Even without doing programming, it is possible. Like you said, there are softwares which can help us. I'm not fully aware. There are softwares where you can upload the data and mention what are the features, etc. And then the software may have some inbuilt classification algorithms like linear regression, and we can train it and just without doing single line of code. But if you are familiar with some basic coding, what is easier is if you are familiar with Python, there is one popular library known as scikit-learn. So scikit-learn offers various functions where you can directly use the function to give the data to train, and then given a new data instance, it predicts the value. So with the help of, let's say, some Python lines of code, you can do this. But here at this point, the major challenge, you have to have a good understanding of data. So even if you're trying a new problem, you're directly getting some data from somewhere. It is okay to try that without any understanding. But the moment you have a better understanding of data and the features, you probably will be able to come up with new experiments or new modifications so that the model predicts it. Sometimes it happens that you have a data set, let's say, of 1,000 features, and you are getting some accuracy of 50%. Right? You don't know what is happening. If you have a good understanding of the data set, you may be able to look at the data set and say that these features, some like out of the 1,000, some 100 features are not relevant to this problem. Let me remove those 100 features and try with just 900 features and see what is happening. But to do that experiment, you should have a decent understanding of the data set and the problem. Right? So, for example, if I am trying to, so I can, it's not difficult for me to write a few lines of code. But what I am lacking is I don't have any understanding of nano. I can straight away download some data set and try it. But if it is not working, I may not be able to look at the data and say that this is why it is not working. That is the problem with domain knowledge, the knowledge about nanomaterials or your knowledge of fundamentals of chemistry, of physics can help you to rectify that. So to answer your question, there are some software available. If you want, I can find it out and tell you where you can directly try linear regression without writing a single line of code. But if you are able to write a few lines of code, maybe you can take the help of ChatGPT or Gemini to write the code. Then it is not difficult to write a few lines of code in Python and use these libraries like scikit-learn to train and test it.
Design of experiment.
Explain design of experiment.
How it is like to regressional analysis in any point.
Okay, can you repeat that? I got almost.
Regressional analysis and design of experiment we can use research everything like that.
Do you have any problem with your mind?
Like we have how many data we get there. Or can you optimize that data with this use of AI?
Okay. So are you asking you have some data set and you have a problem in your mind? So if you have an example problem in your mind, can you tell me the problem? So then it's easier.
Like how any kind of data should be like for a design of concrete like that, from algorithm like that concrete.
Okay. So ratio of different materials for, you said concrete, right? Okay. So basically, so instead of using the word optimize, we can say that how can we build a model so that we can for a new, let's say for a new construction, what is the ratio to be used, right? So here in this case, what we expect is, okay, we are planning to build a machine learning model, or you are going to predict the strength of the concrete. So you mentioned the concrete with respect to civil engineering, right? Yes. Okay, fine. So you are going to predict the strength of concrete based on the proportion of materials you have used in the concrete. That is the problem, correct? So here, when we say we should have a data set first, we'll assume that some sort of experiments is already being done, and then for different ratio of, let's say, water, sand, cement, etc., we know the strength of the concrete, where the strength of the concrete is measured in some lab using there are some defined experiments to check the strength of the concrete, right? So we know the proportion of these materials or the ingredients and the strength of the concrete, right? Assume that we have some 10,000 different data instances with different proportion of these and the corresponding strength of the concrete, right? So this is the first thing we should have to build a machine learning model with. Once we have this, okay, this is a regression problem. Because why it is a regression problem? Because you are predicting the strength of the concrete as a value. You are not predicting it as whether it is having high strength or low strength. If you are predicting high strength or low strength, it's a classification problem. Here you are predicting the strength of the concrete as a integer or as a floating point value. So it is a regression problem. So now once you have it, you can try training a linear regression model. And when you train a linear regression model, your assumption is that the relation between all this proportion of ingredients and the strength is a linear relation. So if you see that your accuracy is very low, how do you check the accuracy? When you get the training data, so when you have, let's say, 10,000 instances of data, you take 20% of the data as the test data. So what you do is that you take 8,000 for training and then 2,000 for test. So you keep the 2,000. You do not touch the 2,000 data instances. Right? You take the 8,000 data instances and then train the linear regression model. And then now you test with the 2,000 data. How do you test? So you with the help of this line, you predict the strength of the concrete and check how close it is to the non-value. Right? For the 2,000 data, you know what is the strength, but you're testing the model you have built. You see what is the predicted value and see how close the predicted value is with the value you have in your data. If it is very close, that means your model is good. If it is very bad, there is some problem with the model. So since you have tried linear regression, what is the next thing you can do? You see that, okay, there is a problem with the model. You first check whether there is a problem with the data. Then whatever you can do with the data, you may do that. Since you have domain expertise in civil engineering or structural engineering, you may try to do that. And then afterwards, you see, is it really a linear relation? Then you can try some other second degree polynomial and see if it is a non-linear relation. So when you try with that, if the accuracy is going high, that means it is not a linear relation, it's a non-linear regression. So you try with. So that is how you do experiments here. So you have a trained data, you have a test data. With the test data, you see when you make changes in the model, whether that is helping to increase the accuracy with the test data. So this is a typical machine learning experiment is done. Yes, so we can use that data, but if you have to check the accuracy of the model, you need a test data, which you can take this from this training data itself, which means if you are getting some 10,000 training data, you can separate, or you can keep some 2,000 data instances aside. Do not use that in the training. Never use that in the training. And once you build a model with this 8,000 data instances, you try to see what is the accuracy of the model with the 2,000 data instances you have. Right. So in most of the supervised learning scenario, we need to have a test data to test it. But if it is an unsupervised problem, so linear regression is a supervised learning problem. In an unsupervised learning, you don't need a test data. You can do the test data also, but you have certain other metrics to see how good the clusters are. We can break.
Now we shall have a tea break and the session will resume at 3:10. Session resume ചെയ്തിട്ട്
Okay, so let's resume the talk. So we were discussing about this nano material classification. So basically this problem, as we discussed, is classify nanomaterial into silicate, silica, and coating. So here we are using, we are not directly using any features extracted, but we are using some images directly. Right? To understand this better, let's try to discuss, let's have a discussion on the basics of neural network. So when we discuss about neural network, I think the first concept we have to discuss is the perceptron, which you can maybe find many similarities with linear regression, which we have already discussed. So basically, a basic perceptron, a perceptron will have some n features, like we discussed in the previous case. We have n features, and we have a single neuron, or we call it perceptron. And associated with each input, we have a weight. Right? And then what we predict is the output. So basically, at this neuron, the computation, what we do is, which is similar to the linear regression, we are doing a sum of weights multiplied by the input. So sigma wi xi, or w1 x1 plus w2 x2 up to w2 wn xn. So this is the computation we do in this neuron. So this is the basic perceptron. And how do we predict y? So this is not a regression problem. So what we do is we define a threshold. Let's say that threshold value is some 0.5. So if this summation is greater than 0.5, we say that the output value is 1. If this is less than the threshold, we say that the output value is 0. So when we try to understand a neural network, this is the basic unit of a neural network, or this is the basic classification technique on top of which the neural network is built. So we have n inputs, we have n weights associated with each input, and then we take a sum of wi xi, and then based on this activation, let's call it as an activation function. If it is greater than threshold, it is 1, and this is otherwise it is 0. So a typical neural network will look like this, and each neuron will perform something like this. Right? Whatever inputs is coming to it, it adds, it multiplies the weight associated with each input and adds together all the inputs and then compute the value. And there is an activation function. So what we have discussed is just one basic activation function. This activation, there are a few different types of activation functions available. So in a typical neural network, there is an input layer with, in this case, we have 3 features. That's why we have 3 input nodes. And we have many hidden layers, many neurons in the hidden layers. and then finally an output layer. So you may be very familiar with this term deep learning. So let's try to understand what is the difference between deep learning and neural network. All of you have heard deep learning, right? So deep learning is neural network itself, but deep learning is a deeper neural network. So the core capability is that it can pick the essential information from the data for further processing by itself. You may be confused what this statement means. Let's try to understand that better. So in a simple neural network, which is not a deep neural network, we have a training data and probably we have to do some feature extraction to train the neural network. Like in the case we have discussed before, even for band gap prediction, we have a set of features available, or so we know the features. We have a set of property values, right? Which means we have already some set of feature extracted, so on the other problem, when we do CNA analysis, we have a 33-dimension feature where we know that each value is the strength of a CNA atomic composition. So we have some features extracted from the data, or the data itself is some extracted features. But in case of deep neural network, we may not do such a feature extraction. It doesn't mean that in all the problems, given any problem, you can do both. So there are certain problems where a deep neural network will be more helpful. So in some problems, we cannot. It's difficult, or we cannot extract features before we train a machine learning model or a neural network. So in such neural networks, as you see here in this example, it has many neurons and it is much more deeper. Right? In a simple neural network, it may have only a few layers. There is no hard and fast rule that the deep neural network has to have these many layers or something. But in general, we can say that very qualitatively, we can say that deep neural networks are much more deeper than normal neural network. And where it differs is it doesn't need any explicit feature extraction. I know that it is a little difficult for you to understand completely what a feature extraction means. But you have to, so probably maybe the next slides, from the next slides, you may understand that better. Right? So this is what a deep learning, how deep learning differs from neural network. And deep learning is not very different from neural network. There is nothing wrong in calling a deep neural network as a neural network. Right? So to understand our previous problem, let's try to understand a convolutional neural network. For this, let's try to understand another problem, a very common problem of classifying an image as dog or cat. Right? So the data set we have is the images of dogs and cats. Or maybe if you want to go to the previous example of fishes, you can assume that you have a data set of salmon fishes and sea bass fishes, right? So you have a large data set of the images of these two fishes, or here the images of dogs and cats. So we have to train a neural network. Right? So we have some, let's say we have 1,000 images of dogs, 1,000 images of cats. So, but the question is, how do you input this image of dog to this neural network, right? So in the previous examples, in the previous example problems of, let's say, band gap valued prediction, or what is the next problem? The next problem is the structural classification for clustering. We have a fixed dimensional, feature vector, or fixed number of features which are extracted. So in band gap example, we took 3 features, right? We took 3 features and we predicted the band gap value. So in that case, if you are using a neural network, so remember that we can use any sort of, so it's a linear regression problem, but if you're considering it as a linear regression problem with a neural network, this will have 3 inputs, right? But in this case, we have an image of a dog. And how do we give this image of a dog or a cat to a neural network? So that is where this convolutional neural network is helpful, right? So what basically it does is, attached to a neural network like this, we have a convolution layer. So basically what it does is, it scans through some areas of the images and extracts some relevant values. That's what I can say in plain English. So there are some operations like pooling, and then it applies some filtering, etc. But basically what it does is, it scans through the image, and it is able to extract some representative values of the image. And with the help of weights, it will be able to give weightage to the relevant features, right? So when you have large number of 1,000 images, and when we do such a learning, it understands what feature has to be given more importance. So that is how a convolution layer helps in extracting the features from an image. So coming back to the point, how a convolutional neural network differs from a normal neural network is, normal feed-forward neural network is, a convolutional neural network will have a additional convolution layer like this, which helps us to serialize the features from an image, right? So after it does this, finally we can flatten it to a n-dimensional vector like this, right? We can flatten it to a vector instead of a matrix. We have so in the input image is a matrix, a 2D matrix. Sometimes if the RGB, when we use RGB values, it can be a 3D matrix like this. So we extract some relevant values and give some weights, and finally we have a single vector which can go directly to a normal neural network. So in all the image classification problems, generally, I'm not saying that all the image classification problem, generally in an image classification problem, we use a convolutional neural network to extract the relevant features out of an image like this, and then it is passed to a normal neural network, where all sort of multiplication with the weights happen, and then activation functions are applied again and again, and finally it classifies. So it has 3 output layers, which means there's a 3-class classification problem. It classifies the input as some 3 class. Anyway, in case of dog and cat, it is 2 class, but in this, whatever image I have picked from Google search, I just want to. So this is the purpose of CNN, or convolutional neural network, in image classification. So now let's go back to our previous problem. So here I said we are using high resolution TEM images capturing the complex internal structure of nanomaterials, right? So what we have is a data set of images. So they say that the methodology is based on convolutional neural network. So basically they have a convolution layer before the neural network, which extract the relevant features out of the TEM transmission electron microscopy images, and then that's how it is learned. So in certain problems, the data we have may be some plain images. We are not doing any extra feature extraction out of it. But a convolutional neural network like this will help us to extract the relevant features automatically from the data. If you want to understand how it is automatically, etc., so we'll have to go deep into when we have large amount of data, how it learns, etc. So anyway, that is not very relevant. So given a problem, and we are guaranteed that we get, let's say, maybe lakhs of images of the nanomaterials, then we can straight away go with, if it is a classification problem and we have a manually labeled data of some lakhs of images, then we can straight away try a convolutional neural network based approach. So as part of this discussion, we shall see another problem of defect detection. That is, given a nanomaterial, whether there is a defect, right? So in this case, in this problem, I think I again forgot to cite the paper here. So in this paper, they try to identify atomic defect in 2D materials with a primary focus on this nanomaterial called molybdenum disulfide. Right? So what they have is they have high resolution STEM images of monolayer molybdenum disulfide, and what the dataset has, some experts has labeled each image as whether it has some atomic position or defect, atomic positions and defect sites. Right? Based on the manual labels, we know that whether so there are some images. So there are some images of nanomaterials with defects, and there are some images of nanomaterials with no defects. Right? So some experts have manually labeled it. So here they use again a convolutional neural network based architecture called UNet. So this is a little different from what we explained earlier. So UNet is a non-convolutional neural network based method which is used for image segmentation task. So what is this is an example. This is not an image taken from the paper. This is an image taken from another article where UNet is used for a different problem. So here it is trying to do an image segmentation. That means that what the input image given is an image of a dog and cat in the same picture. So with the help of UNet, it is able to do a segmentation. Like it is able to identify what are the different objects or different animals or things present in the image. So it is able to mask those areas. How this problem is different from the previous problem is, in the previous problem we are trying to classify, or in this problem we are trying to classify an image of a nanomaterial as silicate, silica, or coating. Right? So finally we have three classes. We say which class has got the highest probability. But in this case, in this problem, we are using convolutional neural network, but we are not really classifying at the output. We are doing some sort of segmentation, and then probably there could be another layer which helps us to classify whether it has a defect or not. But this image segmentation with the help of this UNet based architecture is very key. So that I think what they expect is the UNet based architecture will help them to identify the probable areas where a defect is there in a nanomaterial, given nanomaterial sample. Right? So that is how. So what I was trying to explain is there are certain other methods based on convolutional neural network, and problems like segmentation also can be done. So this defect detection was just an example. So if there is another problem where given some mixture of nanomaterials, you want to find certain whether the presence of certain nanomaterials is there, or identify the places where those nanomaterials are there, probably such an approach could be useful. Right? So if you have large amount of data with images of mixture of nanomaterials, and then you have manually annotated labels or manually annotated segments, with the help of this you can use some networks like this. Given a new image, it can identify where, at which places or which positions certain nanomaterials are present. I was just telling some hypothetical or problems where so such an approach could be useful. Okay, so in fact, I'm done with that the technical content, but let me try to answer this question: can I do research in nanomaterials and AI, applying AI? Right. So maybe this could be probably one of the questions as a sub questions under that. So I have expertise on nanomaterials. Can I do research on problems involving AI? Right. So this is one question you may ask. Again, in continuation that you may ask, do I need to know machine learning? Right? So the answer to the first question is definitely yes. If you have some expertise on nanomaterials, you can identify a problem and do research involving AI. And do I need to know machine learning? You may have to know eventually, but to start with, you don't have to know. So am I supposed to have good coding skills? Not really. So let's let's try to see. So let's try to. So these days, so if you ask me how I didn't have any knowledge of nanomaterials. Even I didn't know the proper definition of nanomaterials before starting to prepare for this talk. So I basically make use of the existing large language models, including ChatGPT, Gemini, to get a better understanding, because a Google search also could be helpful, but given the limited amount of time as a faculty member, this could be more useful, because we can ask follow-up questions about the responses it gives, and it makes things faster, right? So in such cases, these large language models can be helpful. So let me try to introduce to you how the large language models like Meta, Facebook's Llama, or even ChatGPT can be helpful. Can you tell me an example problem where you would like to do research? Let's try to see how we can. We will go with your question. So we'll do a 15-minute session to understand how these resources can be helpful in doing research. You can say some example problems, maybe in nanomaterials or in some other field as well. That's okay. How to?
Properties of a membrane.
Of a membrane.
Better oil absorption.
So we are starting with a very plain question, right? So we are starting with a very plain question. Maybe some of you may be familiar with how to make use of this, but let's try to see how we can engineer the prompts properly, so that we get some desired answers, and how we can use these resources as guides to give some directions. So when I asked this question, okay, give me some guidance on how to involve machine learning in the following problem. So because when we just state the problem, even I don't get any idea about how to involve machine learning. So what is the data here? How do we? Is there a possibility of training something? So it says that identify the key membrane properties. I didn't have, anyways, Sonu sir may have is aware of these properties, but if I am searching for this problem, I don't know about all this membrane properties. It says that these are the membrane properties. Now, if I want to know more about membrane properties, you can search for what is membrane properties, right? And then collect and pre-process data. Right? This could be difficult, because anyway, if you don't have access to data, that's a problem. But if there is an existing data, you can now find out if there exists such a data. Then feature engineering, extract relevant features from data. So now the point is that we were at this state of what we have with us is we just know the problem, right? When Sonu sir mentioned this problem, I didn't have any understanding of the problem, but after reading this, we now have a better understanding of how to proceed. Right? So now, anyway, this is a little difficult problem, but let's try to see, is there any existing data set for this problem? See, we are getting more information. So it is giving some references, 1 and 2. So it is giving Bing search. Okay, that may not be helpful. So we are getting this results here because this is normal. If we involve deep research is actually an aspect of large language models which help us to search from existing papers and other research resources. We are not doing that here now. See, we are getting some more information. It's not giving any data set. Maybe there is no data set existing for this problem. Okay, so let's assume that we search for a problem for which a data set is available. So, but you don't know how to start the coding. Right? Then, anyway, this is little risky in the sense I'm not guaranteeing you that it will give you the code. It will give you the correct code. Give me a working code which can help. It's even able to generate a code for us. So even if you have only limited coding skills, so if you can generate a code like this, and then if you have the basic skill of reading the code and understanding it, probably you would be able to start with some experiments. Right. So if you try with, so there is another platform called perplexity.ai. So let's type the same problem there. In perplexity.ai, if you have a pro subscription, I have a pro subscription because NIT gives a pro subscription here. Pro subscription for perplexity.ai. So I have selected deep research. So this is called deep research. So when I give the problem there, it takes some time because here it is different because it's not simply generating some text. It is looking into some existing literature and other research related resources to identify related papers. And this is more, we can trust this information better. It gives some, it gives better information which we can trust because it's directly from some sources. Okay, so you may ask where it is helping, or is it ethical to do this kind of search, to do research? As long as we have the creativity, the creative element, we are not, this is not doing anything creative. So we may also probably do the same if you sit for one full week searching for papers, etc. for the problem. We may also do the same. We may end up with the same results. But the advantage is that you are not spending 1 week. Instead, you are spending less than 1 hour for this. Right? But the creative aspect of research anyway has to come from you because you have to come up with new ideas to do the research. But the advantage is that whatever is existing, it is easier for you to identify, and you may not reinvent the fire again, which means you may not do something which is already existing. The probability of you doing something existing is very less because identifying, and if you identify a method, you can say that this is my idea. You can search for whether this idea exists or not. Then this is able to identify whether there is some already existing papers which have tried some similar experiments. See, this is giving better idea. It is even saying that we can use support vector machine. Support vector machine is it's not a machine. It is a machine learning classification. It's machine learning algorithm. This is giving some good number of approaches and then how to start the experiment with. So here the advantage is that it's also even sideways. See, artificial neural networks for predicting the diameter of electrospun. So is this paper related? It's a paper published in Materials. Is this paper related to the topic what you mentioned? So at least it is even if nothing happens, at least it is able to find some relevant literature to the problem which we are searching for. Perplexity has a free version, but now I am using the deep research, I think, which needs payment. But NIT Calicut is giving that for free to the students and faculty. I don't know whether there is some limited access, but to some extent it is helpful to me. So if there is some existing literature, it gives that. Also, it is able to summarize what are the existing approaches, or it is able to summarize what are the possible approaches. Right. So if you when it started, you could see that it was. If you look at the steps, see these are the steps it did to get this understanding. So it searched, it read some 20 sources, some papers relevant. It identified some relevant papers. It actually did a search in these relevant papers. And then, so if we manually do this, probably we'll do this for 1 week and do the same. But this manual effort is reduced. There is nothing wrong in doing this, because otherwise, definitely people in China would do the same. Right? If you're not using these resources, that is where China has got an upper hand in research, because they make use of tools and they don't mind working hard for long hours. That's why they are able to so even many of the US universities, I think they are more interested in recruiting PhD students and postdoc candidates from China, because they are guaranteed. So it is guaranteed that they work hard. So it is. So what we have to do is that we have to probably make use of these resources better, so that we can advance our research faster. With yeah. Okay, if we have a data set, okay, I assume that. So are you saying that you have a data set, but you don't have a relevant problem? Right. Yeah. Okay, let me take an example approach. Assume that you have a problem, right? You have a problem and you know the data. So what you can do with this Perplexity, or even with Gemini, or Facebook's Llama or Meta AI, what you can do is you can mention the problem and then probably give details about the data. Right? If it has, let's say we know that the data set has some 10 features, we just copy and paste the features in Llama and say that, see, these are the features. What are the approaches you can suggest? And this is the problem. What are the approaches you can suggest with this? So if you give, so basically whatever information you have, if you are able to give that information to these tools, it will be able to process and give you a better response. Okay, maybe a dataset won't be a Python program. The dataset would be some tabular data or some text data or maybe some values, etc. So if that data is available, you can. So you may even can provide some samples of sample data to these tools. To directly to these tools. So you can see these are the sample values. Then it may do some it may do some analysis, like, for example, if there is a field called atomic composition, which is some there are some text, right? It is this composition, this some name to the atomic composition. So this gets an understanding that, okay, this particular feature means it is it's a text value. Right? There is a name to this. So based on that, it may be able to give you some direction what kind of models is more helpful. Right? So I'm not able to give a very precise answer, but in short, the more information you give to the system, it will be able to give better response. When you give, let's say, 100 instances, you have a 1 million data instances data set. If you give, let's say, some 100 samples out of it to the large language models, then it will be able to say, see, based on this data, I understand that these are the range of values and the mean of these values is this. So probably you may be able to, it looks like a linear regression won't work here because of these relation. It may be able to tell us all this information. Yeah, sure. That won't be directly possible because assume that you have some images and you have so it is not really possible because these models may not be able to interpret images to that extent. If you upload an image of a dog and ask it what the image it is able to say that it is an image of a dog. But assume that you have an electron microscopy image of some nanomaterial, and it may say that it looks like it's some electron microscopy image, but I don't understand what it is. So we shall not expect that much expertise from this. But if you have some values, etc., it will be. If you give if you upload the image of, let's say, Narendra Modi or Donald Trump, it will be able to say that it is Donald Trump or Narendra Modi. The reason is that on the web there are large number of images of these people, right? So it is able to say if you upload my image there, it will say that he is some human being from India. That's it. It may not be able to predict. It may not be able to tell anything further. But when you so the point is that whatever information is there in abundant on the web, these models are able to say, or whatever conclusions it can make, right? Why it is able to say that when we give some data, it says that okay, linear regression may not be applicable. You may have to go with higher degree regression because it has seen many such problems and many similar data. Right? So that is why it is able to say that this may be applicable. So what we have to keep in mind is it is a again, this large language models are statistical learning based tools in the sense it is trained with large amount of data, right? Large amount of data, and it has the capability to look at resources from web and take conclusions from that. So so its understanding is limited to that. But it is okay to try that because probably we may get some conclusions which are useful to us, which we might not have think about it. So coming back to this. Okay, so then we felt that okay, in this problem, okay, let's see. We assume that we have a data set. So then I say that okay, I want to try neural network on some data set for this. Can you give some sample code? So it is now searching. See the resources it is searching on. So it is searching a large number of papers and some articles, right? So based on that, articles are some coding articles. You can see that convolutional neural network on TensorFlow, introduction to artificial neural network in Python, Keras with TensorFlow prerequisites. It is searching. So it is trying to understand the problem. It is trying to understand how to code. And now see, it has come up with the code. Sometimes there could be some problems, but by looking at this code, you have fair understanding. So probably if you start coding with this, it may take, even if you are a good programmer, it may take 2-3 days to code this. But now you have something to start with, and you just need to make changes to this code. So as a researcher in chemical engineering or chemistry, you are not expected to have expertise in coding. So it is okay to try with this code, and then finally you may have to do some verification just to make sure that whatever you're getting is correct. That's it. So it has come up with a nice code. I think this code you may take at least 2-3 weeks to reach this point. And now the advantage is that now you can run this code, see the problems, and then keep on rectifying it, which doesn't take some time. which doesn't take time. Otherwise, the learning curve to start coding something like this is a little, it takes some time. Right? So we may have to understand. So they have used this library called yes, TensorFlow, Keras, which is built on top of TensorFlow. And with limited understanding of neural networks, it's a little difficult to code this. But now you can try with this and then see what is happening. And now if you want to, so let's say, even if you know that, okay, you understood that there is something wrong in some line, you don't know how to change it. You can say that, see, I feel that there is some problem in this line. You can type that, I see there is some problem in this particular line, correct it. Sometimes it is able to correct. So with these interactions with the large language model, sometimes your research can be made faster. And maybe you can reduce the number of human resources required for your research, and then make the same thing happen. So with this, shall I conclude, or if you have any questions, I can answer. So anyway, I was describing this within the scope of applying machine learning, but remember that you can do it for anything. Right? You can whatever research you do, to ensure that you can even check the validity of your idea. Right? Basically, so basically how we do that, we have an idea, we keep on searching for papers, we go through the papers and make sure that our idea is in line with that. Right? We use our own analytical thinking skills to come to a conclusion. So with this, it is to some extent shared. So if you ask me whether this will make us lazy and it will affect our thinking power, I'm not sure. I'm not responsible for if something happens to you, happens to your thinking capabilities by using this alone. Anyway, I don't know much about it. But what I know is that this can make you, help you to make your research faster. So if you have an idea, you can at least, sometimes when you get an idea, for the first thing, what we have to do is that, is my idea has some validity, or there is some big mistakes within the idea, right? So what this will help us to understand is, if there is some major problem with our idea, definitely these large language models will help us to understand that, because with the help of some references, it will be able to identify that. So it can help. It can help to do the sanity checks on our idea, or whatever methodology we are planning to. So if we are, for example, otherwise for a research, we are designing a methodology, we are designing an experiment. You can type the same experiment here and see whether that experiment is meaningful with respect to the problem statement we are exploring. Yeah, this is to some extent just for verification. We are getting an idea. We are not sure whether we should pursue it, so we can take a decision within a day. Otherwise, probably we may do some experiments based on our design, and after 1 or 2 weeks, or maybe after a few months, we come to a conclusion that there was some problem with the experiment. So we'll be able to take a very early decision with the help of these tools. So what it does is that, assuming that we have large amount of resources and we ourselves cannot go into each resource and come to a conclusion, this is helping us to do that. That's it. It's not very reliable. It's not 100%. But the thing is that sometimes, based on the conclusions it gives, so it also gives reasons for its conclusions. Right. So based on these reasons and conclusions, we are able to judge whether it's reliable or not. So as you said, for example, for the problem you mentioned, if I am doing it, if I am trying to identify the validity of some ideas within the problem, I may not be able to check whether it's reliable or not, because I don't have the domain expertise. With your domain expertise, you will be able to conclude whether the conclusion this gives is valid or not.
Solar electricity look at the statement.
Yeah. Which other? Is it a nanomaterials related question? Then probably we'll have to ask Soni sir. Sorry. In fact, I don't know. Huh? Oh, the AI to detect nanomaterials. Detect. Okay, so I have not explored any problems on detecting nanomaterials, but maybe this is my understanding based on. So maybe if you are doing that with the images of nanomaterials, probably as I have mentioned in the previous case of previous example of this one, nanomaterial classification. We'll have to have large amount of images of nanomaterials, and with the help of these images. So the assumption is that, let's say we have some nanomaterial, we have some image of nanomaterial, a few nanomaterials, and they have some compositions. And from the image, our learning algorithm, neural networks or some algorithm is able to understand different attributes of this image. So based on that, when we present a new nanomaterial, it won't be able to say what is exactly the name of the nanomaterial, but it may be able to predict the atomic composition of the nanomaterial, because there may be images in our data having similar atomic compositions, and it has some direct correlation with the electron microscopy images of those nanomaterials. If that is there, when we present the electron microscopy image of a new nanomaterial for which we don't have any data instance in our training data, since there are similar nanomaterials in our data, it is able to say that this could be having the compositions of these atoms in this way, something like that. Right? So basically, in such problems, you may have assumed that the data is images. Sorry. Okay, I'm not really compared. So I think so. Generally, people use ChatGPT. I think ChatGPT is very good, and also it depends upon if you have a paid subscription. Some of this performs very well, but for the free subscription for so I don't have any paid subscription on any of this except for Perplexity of AI because NITC is giving that. Otherwise, I am not. Sometimes I have given the same query to multiple LLMs. But I'm not in a position to compare. So some people say that ChatGPT is much better. I felt that Gemini from Google is also better, also good. But we will have to compare. We'll have to compare on a case by case, on a case base, because for certain problems things work. So we should be in a position to conclude which one is better for a particular problem. So if you say that, okay, so for 10 of my queries, Gemini is performing better, but it doesn't mean that for the 11th query, Gemini performs better. Maybe ChatGPT can be better.
It's create because that if together we are very difficult to get that limited time.
Oh, is it? Okay. Oh, okay. That I have not observed. Yeah, maybe that may be similar. It takes time. So I use mostly Gemini and Llama is basically meta.ai, which is from Facebook. I rarely use ChatGPT. So I think when I compare these two, they are almost giving at the same speed. But it depends on the query also. If our query is very complex, definitely it takes time. Okay, after getting the data set, yeah, so that is where we need to have some, we need to employ some code to process the data. So if you have a data set, I think in those cases, these large language models are very helpful. So if you assume that you have some data set in some file format. Let's say it's an XML or maybe some comma separated file. It's a CSV file or maybe some Excel file. It may be a little difficult for you to write a program to extract each field, etc. Right? So with the help of some Python program, it is easier to do that. And the thing is that with the help of these large language models, you can say, see, this is I have a data set in this format. It has these many fields. Give me a code to extract these values so that I can use it for machine learning. It will give you a nice code. Is that your question or something different? Okay, got it. I got it. So you're referring to this data. So, okay. Okay, this assumes that we already have some data in some file format. Let's say it's an Excel file or a CSV file or there are some other file formats also. So we have to give that input to this, saying that, see, I have data in this format and I have these fields in the data, something like that. Or we can even upload the data as such to this. See, you can see this clip. You can attach the file here. And if the file is not very large, or you can take some part of the data and upload it here, and then say, right, give me a program, give me a Python code to extract the features or get the values from this data. It will directly give. I understand your confusion because since you don't have the experience of executing a code like this, you're trying to understand how, when you execute, what will happen, right? So my suggestion is, just try with a code like this, and then you'll get a good understanding what is happening. No, it won't be like that. So here, okay, yeah. So it won't be a text like that. So here, when we try certain queries here, you are getting text as output, but these programs are not intended to do that. What we are going to do is that we have some features, and we are going to train a model, right? Finally, we have even though we say the word model doesn't mean anything. It is just a few values stored somewhere. So there would be provision to use the model within the code. Right? So I know it's a little difficult to answer that question. Probably I can do a demo of how we do that. Then you will get an understanding. Right? It is little difficult to answer this question verbally, but if I give you a demo, you'll be very clear about it. Okay, thank you very much. Anyway, it was a nice experience talking about a very different topic. Thank you. Thank you for your cooperation.
So we had came close to this enlightenment session. It's time to take a moment to